Okay, so welcome back to the Bragg seminar. This week, it's my pleasure to introduce my colleague, Carolina Araujo from IMPA, and she's going to talk on higher Fano manifolds. So please, Carolina.
Thank you, Eduardo. Thank you, everyone, for being here for this talk. Okay, so today I want to discuss this higher Fano manifold. So these are going to be properly defined. But the idea is that we are going to explore some conditions on the positivity of the tangent bundle of projective manifolds and understand what are the geometric properties that these conditions impose on the varieties. So let me start with the general setup. So usually we are going to be concerned with complex projective manifolds. And the Fano condition is a positivity condition on the tangent bundle. So let me recall that the tangent bundle of X is a vector bundle that is defined on X. So we assemble all the tangent spaces, the different tangent spaces at X in a bundle. And we define the anti-canonical class of X as the first Chern class of this tangent bundle. So this is an element in the second cohomology group, or maybe we like to think of this is a divisor class on X, and we're usually interested in the properties of this numerical, or the numerical properties, or the positivity properties of this divisor. So this means that whenever you have a curve, a complex projective curve C on X, we can intersect it with minus K, with the anti-canonical class, and this is going to be an integer. And this number actually is up to a normalization of 1 over 2 pi. This is the average of the Ricci curvature of X along C. So the anti-canonical class is a way of measuring curvature of our complex projective manifolds. Okay, and then the Fano condition is defined as follows. We say that a complex projective manifold is Fano if the anti-canonical class is ample. And in particular, this implies that the intersection with every curve is positive. So, for instance, for curves, this notion, the canonical class, gives us the usual trichotomy. We divide the smooth projective curves into these three well-known classes: positive, zero, and negative curvature, or genus 0, genus 1, and higher genus. So this is this trichotomy is given in terms of the sign of the canonical class, and so the ones that I mostly, the Fano ones are the ones exactly those with the genus 0. Okay, in general, in arbitrary dimension, let me just give you some examples of Fano manifolds. So we have the projective space, probably the simplest example of a Fano manifold. Hypersurfaces, smooth hypersurfaces of small degree, and I'm going to be discussing those in more details soon. Homogeneous spaces, more particularly rational homogeneous spaces, and again, I'm going to be discussing them in more details soon. And also, let me just mention that several moduli spaces are in particular Fano manifolds, especially moduli spaces, say, of vector bundles, usually often are Fano manifolds. And just as a remark, the importance of Fano varieties has been made clear with the minimal model program. So the minimal model program tells us that every projective manifold is built up from varieties with either with minus K positive, 0, or negative. So these are sort of the building blocks for projective varieties. Let me just point out that here for the minimal model program, actually we cannot we cannot avoid singularities. So this, when I say that every projective manifold is built up from the ones on these three classes, we have to allow for some singularity. So often people study Fano manifolds allowing for certain singularities, but in any case, in this talk, singularities are not going to play any role, and we are going to be interested in Fano manifolds. So let me start describing. So what are, if you look at these three building blocks, what are the special properties of Fano manifolds? So I will describe some geometric and arithmetic properties of Fano manifolds. So let me start with a geometric property by looking at smooth hypersurfaces. So if you consider XD a smooth hypersurface of degree D in projective space, then you can compute easily its anticanonical class using the adjunction formula. And so this is the anticanonical class of a hypersurface of degree D in Pn. And so it is obvious that then it is hypersurface is Fano, if and only if the degree satisfies this inequality. D is less or equal than N. And what are the special properties of smooth hypersurfaces of small degree? So it is a very easy exercise. So we are doing this in my next Algebraic Geometry 1 class. It's something that is very easy to check, is that if the degree is at most n-1, then X is covered by lines. If the degree is one more, n, then it is still Fano, but it's no longer covered by lines, but it's still covered by conics. So it's this again, it's a little bit more complicated, but this is it's also something that one can prove, that they're covered by conics. On the other hand, if D is at least n+1, then there is no rational curve through a general point of X. And so this is a very different behavior. If you fix a general point, you will not find any rational curve through that point. And so what we see, the conclusion is that for smooth hypersurfaces, the Fano condition is equivalent to the condition on the degree being less or equal than n, which is equivalent to the condition that the hypersurface is covered by rational curves. Okay, so this is the first special geometric property of Fano manifolds that I want to discuss. And what we will be interested in later on are the sort of generalizations of this condition. So under which conditions, for instance, we could conclude that a variety is covered by rational surfaces, for instance. But okay, but let's discuss this later. So for now, let me just say that this is a general property of Fano manifolds. So this was a theorem of Mori in 1979. He proved that every Fano manifold is covered by rational curves. So this is not special only about hypersurfaces, it's more general. And even strongly, there is this theorem of Campana and independently Kolarmia-Ukamori from a few years later that say that Fano manifolds are more than just covered by rational curves. They are what we call rationally connected. So that means that through any 2 points of X, there is a rational curve connecting those. So this is how we picture it in this way. And in contrast, projective manifolds with the anticanonical class non-positive do not contain any rational curve through a general point. So this existence of many rational curves really distinguishes Fano varieties among the other two important classes. Okay, so this is the geometric condition, and now I would like to discuss an arithmetic property of Fano manifolds. So this is another special property of Fano manifolds, is given by the theorem by Sen from 1936. So Sen proved the following result: if B is a complex algebraic curve, and if pi from X to B is a family of hypersurfaces of degree D in projective space, So we have a family parameterized by a one-dimensional base. And what Chern theorem says is that if the degree of the hypersurface is bounded by n, so if it's a Fano hypersurface, then this family admits a holomorphic section. And so this, in other words, so this is often referred to as an arithmetic property, because another way to state this is to say that if you can view this family as a variety defined over the function field of B. And what this theorem is saying, that if you have a hypersurface of degree d less or equal than n defined over the function field of a curve, then this variety admits a rational point, which is exactly given by a section of this morphism. And again, this has been greatly generalized, and the sort of the ultimate generalization of this result is this theorem by Brauer, Harris, and Starr. It's a celebrated theorem from 2003, and it says that if you have a family of rationally connected varieties parameterized by curve B, again, you always have a section. So pi admits a holomorphic section, or in other words, a rationally connected variety defined over the function field of a curve always has a rational point. So this is a sort of an arithmetic result. And I just want to point out that this, in a sense, is the strongest possible result. That in a sense, this is the best one can generalize sense result. So this is the ultimate. One cannot prove anything stronger than this. This can be made somehow formal. There is a result by Brauer, Harris, and Starr and Mazur that say that there is a converse to this theorem. And now what I would like to discuss is that what if we want to generalize this theorem and consider families parameterized over higher dimensional bases. So for instance, if you have a family over a surface, what are the conditions that we should put on the fiber in order to get a section? So for the original theorem of Chern, that has been generalized by Lang. So now this is known as the Chern-Lang theorem. And the generalization to higher dimensional bases go as follows. So if B is a complex algebraic variety of dimension k, and if you have a family of hypersurfaces of degree d parameterized by this base B, if the degree of the hypersurface satisfies this condition, if d to the k is less or equal than n, then pi admits a meromorphic section. So if you are working over higher dimensional bases, you have to increase here, to strengthen here the condition on the degree, but you still have existence of sections. And now I would like to now pose a problem, a general problem, which is now we would like to, just like the Brauer, Harris, and Starr generalized sense theorem, we would like to find a suitable generalization of the Chern-Lang theorem. So the problem is to find some intrinsic geometric conditions, which I will denote by FK, so this sort of stands for, say, higher Fano conditions, such that, well, we want that for hypersurfaces of degree d in projective space, our condition Fk be equivalent to the condition in Chern-Lang theorem, that d to the k is less or equal than n. And we would like to get we would like to generalize previous results about Fano varieties. So for instance, we would like that projective manifolds satisfying conditions Fk are covered by rational k-folds. And we would like that the Chern-Lang theorem holds if the fibers of the family satisfy the condition Fk. Here, I should put just a disclaimer that this is modulo Brauer obstruction. I do not want to say much about this in this talk, but I just want to say that in general, if you're looking at families over higher dimensional bases, then in addition to a condition in the fiber, you can associate to such a fibration a Brauer obstruction. So this obstruction always vanishes if the base is a curve, but as soon as the base is a surface, you may have non-vanishing Brauer obstruction, and that may be an obstruction to have in a section. So I want to ignore this. So if Brauer obstruction exists, even if you have, say, a family by projective spaces. So this is something that really one has to look at. But modulo Brauer obstruction, we would like to find conditions on the fibers for the existence of a meromorphic section. And so, for instance, we can take the condition F1, so when the B is one-dimensional, to be Fano, or more generally, to be rationally connected. But already for k equals to 2, it is already not clear what the best condition should be. So for k equals to 1, the Graeber-Harris-Stoy theorem gives us the best possible condition for F1 to be rationally connected. And already for F2, there have been different approaches and pointing in different directions. And this is what I would like to discuss today. Okay, so let me start by looking at the case k equals to 2. And in general, I will propose a condition that should be taken, that could be Fk. So again, we are going to look at the tangent bundle of a complex projective manifold. And instead of looking at just the first Chern class, we look at the kth Chern character of the tangent bundle. So let me remind you what the Chern characters measure. So just as an example, let us look at the Chern character of a vector bundle that is a sum of line bundles. So if E is a direct sum of the line bundles L1 up to LR, then the kth Chern character of E is just the sum of the first Chern classes of each one of the factors to the power k. So, so this is a codimension k class in X, and we say, so this is a definition for this talk. I don't think that this is a too standard a definition, but we say that X is k Fano if all the Chern characters from 1 up to k are all positive. By positive, I mean that that it has a positive intersection with every k-dimensional, with every i-dimensional cycle. So for k equals to 2, this was introduced by de Jong and Starr. And more generally, Ana Maria Castravet and myself have looked at the case, higher case more recently. And for smooth hypersurfaces, okay, this is the easiest thing one can verify. For smooth hypersurfaces, it's very easy to compute the Chern characters of the tangent bundle, and we see that it is k Fano. For smooth hypersurfaces, being k Fano is equivalent precisely to the degree condition in the Sendlang theorem. So this is a very easy computation, and in a sense, okay, this is sort of trivial and naive. And now, of course, the other properties are the ones that are hard to check, and the ones that one is most interested in. Okay, so so this is sort of one possibility to consider, say, the Fano. But as I said, the answer to the problem that I proposed have been considered. So there have been other approaches, and I'm going to discuss them. But before I do so, I would like to get some inspiration from topology. So let's consider the same problem, but instead of considering it in algebraic geometry, I want to consider it in topology. So what is the analogous problem in topology? well, this could be a translation. Suppose that you have a fibration of CW complexes with typical fiber F over a base B of dimension K. Then, if this typical fiber F is K minus 1 connected, then pi admits a continuous section. So let me remind you what K minus 1 connectedness means. So if you have any topological space F in a base point P, you can look at the loop space at P, and you can put the compact open topology, and so that this gets the structure of a topological space as well. And then we define inductively the kth homotopy group of F as the K minus 1 homotopy group of the loop space at P with the compact open topology. And so the first, the pi naught is just a set of path path connected components, but already for K equals to 1, this has the structure of a group. So this for K equals 1, this is just a fundamental group of the space. And then we say that F is K connected if all these homotopy groups from 0 to K are all trivial. And so this is the definition of connectedness. And so, for instance, we say that for a fibration over a one-dimensional base to admit a section, we have to require that F is path connected. So 0 connected is just path connected, 1 connected is just simply connected, and so on. And now what I would like to notice is that so the answer of the problem in topology is very well known. And what I would like to notice is that actually this gives us an approximation to a possible answer in algebraic geometry as well. So let me explain this. Now we are going to build a dictionary between the topology and algebraic geometry. And then we are going to reinterpret this topological results and try to translate them into algebraic geometry. So the dictionary goes as follows. So whenever you see a topological space F, you replace it by a projective variety X. And whenever you see the interval, the path, you replace it by a rational curve, CP1. And so the answer to the problem in topology for the problem for K equals to 1, which was F is path connected. If you translate using this dictionary, you get exactly that X is rationally connected. So any 2 points of X can be connected by a rational curve. And this was exactly the solution to the generalization of Tsang's theorem given by Graeber, Harris, and Starr. So actually this was also the ultimate solution also of the problem in algebraic geometry. So now let's see what we can do for K equals to 2. So for K equals to 2, the solution in topology is that F is simply connected. So path connected plus the loop space at the point P is also path connected. And so how can we translate this into algebraic geometry? Well, so this, let's see, that F is path connected is simply that X is rationally connected. But now, how do we translate this condition here? The loop space itself is path connected to algebraic geometry. So first of all, how do we translate the loop space? So if you in topology, if you fix a point and you look at the loop spaces at point, the first thing that we did is we gave a topology to this set. So we gave the compact open topology to this loop space. Now, what about in algebraic geometry? So of course here, what we could do is, as objects, we are looking at rational curves passing through P. But of course, that this does not have in general a structure of projective variety. So for instance, we have, for each degree, we will have different components. So in general, there is a scheme that parameterizes rational curves through a point. This is a well understood and well studied scheme. However, in general, it has infinitely many irreducible components. So it's not going to be a finite type. And so it's not a projective variety. And in general, it will not be rationally connected. Well, in particular, because it has several irreducible components. However, there has been an approach, tentative analogous to this to the loop space that has been considered in algebraic geometry, which is instead of just looking at all rational curves through a point x, let's just look at the rational curves, say, of minimal degree. So among all the rational curves that pass through a fixed point x, I just consider those of minimal degree. So by this minimality, that itself will be a projective variety. So now we get something that is proper. It's sort of bounded, and then one can hope that, say, well, maybe then we can ask that this space is itself, this space of rational curves of minimal degrees, rationally connected, and these conditions have been used and have been investigated. But here maybe I want to point out that this analogy with topology has limitations, and I just want to explain very briefly one limitation of this analogy, which is that in topology, if you, for instance, if you want to prove this statement, this for instance is done in Hatcher's book. If you want to prove this statement about the existence of sections, one thing that you use in the proof is that if instead of looking at the loop space at a point, you consider the space of paths connecting 2 points P and Q, these two spaces are homotopy equivalent. So you can go from one to the other. So that means that just making assumptions about the loop space at one point, can tell you about things about the loop space, say, of spaces of paths through 2 points. And this is very much used in the proof. While in algebraic geometry, if you want to use the same proof or try to adapt the proof to algebraic geometry, then this becomes a serious problem, because if you know properties, say, rationally connected about spaces of curves through a point, then if you now look at, say, spaces of rational curves of minimal degree passing through 2 fixed points, so now the degree here, of course, we'll have to increase. This minimal degree is not the same, but you can say, so now you want to study spaces of rational curves of small degree through 2 points, then it's not easy, it's not automatic to completely recover it just by knowing the space of rational curves through a point. And so this difficulty is, so this is a difficulty in algebraic geometry. Nevertheless, this analogy has been explored. And there has been, several notions, it's not yet stabilized yet, notions of what now people call rationally simply connected. So let me just give you an approximate definition of this. So we say that a complex projective variety is rationally simply connected if, both x and the spaces of rational curves of minimal degree through general point are rationally connected. We often ask that some version of the spaces of rational curves through 2 points is rationally connected. So here I say some version because here, so this depends on the definition. There are several definitions. Plus, often one plug in some extra technical conditions that basically make the proofs work. So this conditions, so actually they do vary a little bit from paper to paper, depending on what they want to prove. And so there is not an ultimate yet definition of rationally simply connected. Nevertheless, it has been this is seems to be an important notion that has been much investigated recently. And so coming back to our problem, so let me just recall that this is the problem that we are interested in. We want to find intrinsic geometric conditions, Fk, such that for hypersurfaces of degree d, satisfying Fk is equivalent to the condition that appears in Sang-Lang theorem, d to the k is less or equal than n. We want that projective manifolds satisfying Fk are covered by rational k-folds. And we want that Sang-Lang theorem holds if the fibers of pi satisfy the condition Fk. And de Jong and Starr have asked whether one can take, so these are two different questions. So we can ask whether we can take F2 to be two Fano. And de Jong and Starr further propose that one can take F2 to be rationally simply connected. So these are two different generalizations, say, of Sang-Lang theorem in this case. So here we are, so again, here this is the definition of a K-Fano that I introduced today. So all the Chern characters of T from I equals to 1 to K are all positive. And we've been asking whether one can take Fk to be X is K-Fano. Okay, so this is the motivation that led us to study this higher Fano varieties. And so Ana Maria and myself started to try to understand what are the special geometric features of these varieties. Yes, Raimundo? You have a question?
Thanks. Yeah, so probably I missed it, but did you say that there was a connection between being two Fano and being rationally simply connected? When you have these two equations that are, would imply that equation.
Yeah, so these are, so being a true Fano or being rationally simply connected are candidates for condition F2. And there is also, Ana Maria and I have conjectured that true Fano manifolds are rationally simply connected. Although, and we have provided some evidence, but this seems to be a very difficult problem. We do not know how to solve this yet. We have, and maybe I can go quickly. I can go back to the. Okay, so and. I can tell you what the problem to verifying that a two Fano variety is rationally simply connected. The difficulty is this plus some technical conditions here. So this is something that I'm not stating. So these are very let me say it this way. These are horrible conditions. I mean, the definition is not pretty, and it's even worse. It's very hard to check, and so. So we provide some evidence that two Fanos are rationally simply connected, but we cannot yet prove it. Okay. Okay, but now, so let me tell you what have been our approach to study these manifolds, this two Fano manifold. So we, as I said, what we have been doing is to look at the rational curves of minimal degree through X. And what we have, the first thing that we have done is to understand the tangent bundle of H sub X. So here we proved we computed. The first thing we did is to compute all the Chern characters of the H sub X in terms of that of X. So let me put here fix the notation. So here the H sub X is a family of rational curves of minimal degree. It comes, so this is, as I say, this is a parameter space for rational curves. So it comes with a universal family, which we usually call U sub X. So this is a P1 bundle. So these fibers are all P1. And this morphism here I denote by pi. And there is an evaluation map so that it takes such a fiber here to a rational curve of minimal degree through X. So we have this diagram. And so if you take a Chern class, a line bundle or a tangent bundle, so if you take some vector bundle on X, you can pull back, one can often pull back to U and then push forward to H sub X to construct classes on H sub X. And using this pull back, push forward, we can write down explicitly what are all the Chern characters of the H sub x in terms of that of x. So this is the Chern characters of x that appear here, and this L here. I'm not saying this is what this L is, but this L is a sort of a natural polarization on the H sub x. So the H sub x comes with a natural polarization, with a sort of, it's almost an embedding. And this ample line bundle L on H sub x here also appears in this formula. So all the Chern characters can be written in terms of this sort of canonical polarization on the H sub x and the Chern characters of x itself. And with this formula, then we can actually unveil sort of this recursive structure on higher Fano manifolds. So if x is 2 Fano, you can use this formula to prove that the H sub x is itself Fano. And if x is 3 Fano, again, you can use this to prove that the H sub x is 2 Fano. It seems, so although it seems that if x is k Fano, then the H sub x is k minus 1 Fano. So we proved it in some cases under some assumptions, but we cannot prove it yet in a completely general way. And one should think about this again. With this analogy with topology, there is this recursive structure on this connectedness. So this, in terms of the loop spaces, that somehow is reflected here in this higher Fano conditions. And this sort of inductive structure has been explored with respect to this problem. So for very recently, so for instance, this approach was taken further by Suzuki and Nagaoka. So what they proved is the following. So here, this is what they proved. If you assume that x is k Fano, plus you also need here to assume that the space of rational curves of minimal degree has dimension big enough, then they started to look not only at this. So this by this I mean that you look at the rational curves of minimal degree through x. So this is the H sub x. Now this itself is a projective variety, so you can look at the space of rational curves of minimal degree through a general point on this variety. And then you keep doing this, you look at the space of rational curves of minimal degree, in the space of rational curves of minimal degree, the space of rational curves of minimal degree, and so on, inductively. You can do this, if this has dimension big enough, you can do it this k times and still prove that this is Fano. So this is instead of sort of doing this further, and they use this to prove that if x is k Fano, plus under some conditions that I don't know, maybe a bit technical, I don't want to get into details, then you can prove that x is indeed covered by rational k-folds. So this, sort of it's towards an answer of the original problem that I posed. And maybe it seems that k Fano, it's a good condition to be taken as fk. So this is very promising. That this seems to be a good condition. So we've been investigating it further, and then maybe now I want to maybe say that, okay, maybe this is not such a good question. So maybe the point of this talk is to say that, okay, this is very promising, but now I want to bring you some bad news. Well, maybe not bad news, but some limitations of this condition. And okay, and so maybe the point is that there are very few examples of higher Fano manifolds. And so maybe let's look at some examples to try to see what are the special features of this higher Fano manifolds. Okay, so for instance, let's look at examples of 2 Fano manifolds. So for 2 Fanos, there are, by now there are quite a few examples. So for instance, we have already seen smooth hypersurfaces of low degree. And even more generally, one can find that one can easily classify what are the complete intersections in weighted projective spaces that are 2 Fano. So here this is the condition for hypersurface of degree D, but one can write a similar condition for complete intersection. So this would be the sum of the squares of the degrees should be less or equal than n for the projective space, and the sum of the weights for the weighted projective space. But it's very clear what is that the condition is just a numerical condition on the degree and the weights. And now, what about homogeneous spaces? So which homogeneous spaces are true Fano? So homogeneous spaces are sort of are well understood. So in general, if you have a projective variety, if you assume that it is homogeneous, so that its automorphism group acts transitively, then it is necessarily a product of a abelian variety, the Albanese variety of X, and X prime here. X prime is a rational homogeneous space. So this is in fact, this prime part here is a Fano manifold. And even more, for rational homogeneous spaces, any rational homogeneous space can be written as a product of suitable G mod P's. So here each Gi is a simple algebraic group, and P is a parabolic group. And so let's restrict ourselves to this rational manifolds of the form G mod P. So whenever you have such a G mod P, this can be represented by a Dynkin diagram. So to the G, we can associate a Dynkin diagram, and the parabolic subgroup can be represented by a marking. So we choose. So we have this Dynkin diagrams, and we mark some nodes, and depending on how many nodes we mark, that for instance gives us the Picard rank of the rational homogeneous space. So for instance, let me these are the Dynkin diagram. There are the sort of the classical ones, which is the A, B, C, and D, and we have one for each n, and there is also the exceptional ones, the E, F, and G. And let me just explain to you very quickly what are the ones of classical type. So these are the ones with Picard rank 1. So I'm looking at the maximal parabolic subgroup. So basically I take a Dynkin diagram and I choose one marking. So, and when I choose the marking K, I get the G mod P, the marking PK. So here I'm taking if I take the marking K here, then the G mod P in this case is just the Grassmannian of k-dimensional linear subspaces in n+1 dimensional linear vector space. So all the Grassmannians appear in this way. So the ones of type Bn and Dn are what we call the orthogonal Grassmannian on spaces of even and odd dimension, and the one of type Cn is the symplectic Grassmannians. So these are the classical types, and again, and also the exceptional types are also well understood, the E, F, and G cases. And so here is our result. So basically, what we have done is we've gone through the classification of this marked Dynkin diagrams, and we checked which ones are true Fano, and so we get a classification of homogeneous true Fano manifolds with Picard number 1, and basically this is the list. So for instance the AN. Remember, this is the Grassmannian, and so this is what this is saying here is that so either the marking is the first one or the last one. So this is just PN, or it is roughly in the middle. You have to mark you can mark the ones sort of the. Let me go back to my, so this basically you have, in the case of AN, either you mark the first or the last one, or roughly you mark something more or less in the middle. And so these are the ones that are true Fano. And similarly, we get a classification. So this is the general classification. So these are all the homogeneous true Fano manifolds. And now if you check which ones are 3 Fano, and then and the only ones that are 3 Fano are the quadratic hypersurface and Pn. So actually, let me write down that the only known examples of 3 Fano manifolds are the complete intersections of low degree in weighted projective space, and Pn and the quadratic, which is in particular also complete intersections of low degree in projective space. So we only know complete intersections of low degree as example of 3 Fano manifold. So we know no other example of 3 Fano manifold. So this is why I said that even though those results of are very promising, but indeed maybe this condition is already for k equals to 3 is so restrictive that maybe this is not a good condition to look at. And so maybe what I would like to propose instead is actually, maybe I want to say that this already for the 3 Fano, this is maybe so restrictive that it may in fact give us new characterizations of complete intersection. So let me end by stating, well, this general problem to find an example of a 3 Fano manifold other than complete intersection in weighted projective space. And we believe that this asking that a variety is higher Fano may actually be eventually a characterization of a projective space. So we conjecture that if X is K Fano, where this K is sort of roughly log base 2 of n plus 1. So this is basically, this bound here is what to leave the quadratic away. So this is if X is K Fano for K sufficiently big with respect to the dimension, then this should be a characterization of a projective space. And maybe even more, for each fixed dimension n, we believe that there, one should be able to find the smallest integer k, such that the k Fano condition in dimension n characterizes as complete intersection in weighted projective space. So for the moment, even k equals to 3 independently of n could work. So we don't know. And okay, so this is what I wanted to tell you today. So thank you very much for your attention.
Okay, thank you, Carolina. Okay, are there questions? So Carolina, you mentioned that if X is K Fano, then HX is K minus 1 Fano. But you can only prove this for K equals to 2 or 3, is that it?
Well, we proved it for k equals to 4 as well, under some, we almost prove it for k equals to 4. There is we have to make one sort of one assumption. And actually for all of those, we always have to put the assumption that the space of rational curves is big enough. So maybe this is forced. We believe that this is forced by the higher Fano condition already forces this space of rational curves of minimal degree to be big enough, but we cannot prove it. We cannot prove it even that being higher Fano implies that the space of rational curves to the point is positive dimensional. So this is something that for instance, we checked. We went through the classification of Fano with high index by Mori Mokai, and we checked many of these things in the list by looking at the classification, but we couldn't. But this is actually how we, for instance, we classify the two Fanos of dimension 3 or two Fanos of high index, but we have to look at the classification. We could not prove directly that the higher Fano condition has some implications, certain implications. So this is what it sort of seems to be.
Mm-hmm. But you try to check those conditions. I mean, the k-1 Fano by looking at the definition itself, intersecting with the classes and pulling back and pushing forward classes using the diagram.
Yes. So in this case here, I don't. Let me put it here, and I can put the. I think I have here the formula. So see. Here there are this, so this is the formula for the Chern characters, and you see that there are some negative and positive signs. So it's hard to control this. So this is why it's what we have to do is to sort of rewrite things in a way so that the negative signs get compensated by the positive signs. So, and in a sense also this is what they do here in this work. They have a recursive formula for the first and Chern class of the H's of the various H's of H of H of H sub X. But again, there are some positive and plus signs that maybe there is just one has to write it in a smart way. So basically how we prove this is we wrote this and then we rewrote this equality so that the minus, the minus stuff got compensated by the positive stuff, but we could not do it in general. Yeah.
I see. But it seems from what you say that, I mean, being higher Fano is very restrictive somehow. It's a very strong condition.
Yes.
Right?
Yes.
But HX has less restriction because it's one less. So is it a simpler variety in some sense than X? Can you say it in different ways, or is just this?
Usually, okay. So this is sort of thing. Not formal, but usually the H sub X is a baby of the X. It's very common that if X has a property, mm-hmm. H sub X has a little bit weaker version of that property. For instance, for homogeneous varieties, if X is a homogeneous variety, you can look at the spaces of rational curves of minimal degree through X. In most cases, it's a homogeneous varieties, but sometimes it's not a homogeneous variety, but it's an almost homogeneous variety. It has a group action with a dense orbit, and so sometimes you often have sort of slightly weakened versions of the properties of X get carried out to that of H sub X.
Mm-hmm, mm-hmm. So in a sense, maybe it could be easier to try to understand which H of X could be 3 Fano, for instance.
Right. Yes, and in a sense, this is what we have been exploring to actually eliminate all those cases. So this is exactly how we prove that in the homogeneous varieties, none of them are 3 Fano except the projective space and the quadratic. It's just by applying this argument.
Okay.
Hey, Mundo, you have your hand?
Yeah. So, do you know if you give me a K-Fano variety, do you have any universal construction or some construction to construct another K-Fano variety that may be slightly less K-Fano, say blow-ups for just Fano? If you just start blowing up, you still are Fano, but you're slightly less Fano, and you have some control over this.
Yeah, actually, it tends to be the opposite. So this is okay. So for instance, products. If you have a product, it's not Fano. So this is, in a sense, this is very different than the Fano condition. If you have X and Y are Fano, then X cross Y, the product, is also Fano. But for true Fano, it's not the same. In a sense, if you take X true Fano and Y true Fano, then the product is not going to be Fano. You can cook up a surface where the second Chern character will intersect 0. Basically, something that a line in one cross a line to the other. This one will have 0 intersection with the second Chern character of T. So this is it's much more restrictive. So products will not work. And okay, so we believe, again, this is a conjecture, that all the examples of two Fano varieties that are known have Picard rank 1. And okay, maybe I don't want, maybe today I am not, I'm not brave enough to make this conjecture, but I've done this before. That now maybe I put as a question, but we do not know of any example of two Fano manifold with Picard rank different than 1. So you may not, so there may not be any recipe to cook up different two Fanos from other two Fanos.
So you're saying in particular, for instance, that the converse to this last statement that you're showing there is not true, right?
Definitely not true. Yes, not true.
Right.
Do you gain anything by looking? Oh, I'm sorry, Inder, you want to?
Yes, sorry, I had a question. So you asked, you mentioned the same thing in the beginning, right? So that was also like, I mean, I looked at it from the perspective of C1 fields. So if I understand correctly, that was like the property that they made of the field, and then they said that every hypersurface will have this rational point, and then it was generalized by Lang, Manin, and Collard that you can have it for any rationally connected variety. So, and then of course the question is whether you can do this, I mean, with different characteristic fields. So do you have things like that here? Is there an arithmetic that I'm...
Okay, so I think that it has been, people have been asking questions is it true that a two Fano manifold has a section over a C2 field? But I myself have not looked into this. So this is certainly a legitimate question.
So it is open, and we can ask a question.
Yeah, one can ask that. I think that when De Jong and Starr introduced the two Fano first, they were interested in this kind of problems.
Yes. So I wanted to know if what you're doing now, you can answer more things, you can translate it into this language.
Yeah, well, yes. I haven't looked at in other characteristics, but there are people have been asked this question. Yes.
Thank you. We will talk about this later. So
okay.
Thank you.
Okay.
Thanks for the talk. It was really good.
Okay. Are there more questions?
Yes, maybe it's another question, but I would like to ask anyhow. When you characterize Fano hypersurfaces, can you please come back? It's in the very beginning of the talk.
Okay, maybe. Okay. Wait. I think it was here. Yes.
So I have this, and I guess that maybe you have found only examples with Picard number 1. Is because maybe in your definition you should change, because the polynomial that you define is homogeneous in the sense of the Picard number 1 of CPN. But what happened instead of taking that, okay, probably already mentioned that is not true, but okay, but maybe it can work if you take the product of two projective spaces or a projective toric variety where it's not a product of two projective spaces, what's with Picard number 2. So it makes sense also to consider a homogeneous hypersurface there. Also keeping track, general hypersurfaces in these cases are going to have Picard number 2. It makes sense to define what Fano means in that sense too, right? Picard toric varieties are Cohen-Macaulay, so you can also apply this adjunction formula. So at least for Fano, makes sense to consider homogeneous hypersurfaces in projective varieties with Picard number greater than 1.
Yeah, yes, sure. I mean, so yes, so there are several examples of Fanos of higher Picard rank. So for instance, for toric varieties, there is in the small dimension, there is they are classified, but none of them are two Fano. So as no.
Because maybe the extension, can you please put the definition of K-Fano? Because also you consider it has to be in the projective space, but what about if you restrict, if you allow the definition to live in a different?
Mm-hmm. Okay, so for instance, let me say that this, I agree that this is a too restrictive definition, but maybe it forces the Picard rank to be one. This higher Fano
Exactly.
forces that. But I agree, maybe, and yeah. So as I said, I've conjectured this before, maybe not today, but so this, it seems that now. Okay, maybe let me go on and just mention this condition here that I said that. So this condition, the next condition, this rationally simply connectedness, this condition here.
But could you please?
Let me just show you this, just one definition. Okay. So this one admits versions, this rationally simply connectedness. This admits versions when the Picard rank is greater than 1. So here I do not put what the condition is. I just said that there are some technical conditions, but now there have been some. So there are different notions of rationally simply connectedness that allow for higher Picard rank. So in a sense, this has a better hope of giving you interesting but somehow more general examples.
Yeah, thank you.
Okay. So if there are no more questions, so let's thank Carolina again. And thank you for coming, and see you in next edition of Bragg. Take good care.
Tchau, tchau, pessoal. Obrigada.